Okay, so let's check out our first example here of a power series, and we're asked to find the radius and the interval of convergence. And well, I'm really showing you this whole first piece for the radius of convergence, just the way I laid it out on the page. So here's our power series. Um, n equals 0 to infinity, x to the n over 5 to the n. Um, a power series will always begin at 0 because we want the zero power term, right? So this one, it doesn't quite look like exactly the way it's laid out in the definition, but you can imagine like this is 1 over 5 to the n with the x to the n next to it. And, if I asked you where this thing is centered, it's not stated, but hopefully it's, we can tell where this thing is centered. If we only have x to the n, then it's centered at 0, right? Okay. So let's tackle this radius of convergence. How are we going to do that? So here's what we're going to do. We notice that that series looks like a geometric series. If I rewrite this as x over 5 all raised to the n, then, well, isn't that a geometric series where x over 5 is my radius and my a is 1? Okay, how was that helpful? Because I know for a geometric series, it converges when my r, the absolute value of my r, is less than 1. So here, if my r is x over 5, then I can say, well, absolute value of that must be less than 1 to converge. And here I can quickly isolate the absolute value of x. If I multiply that 5 over, the absolute value of x has to be less than 5. So right there, I can identify my radius of convergence as being 5. If you go back to the definition of radius of convergence, it's x minus c less than r is when it converges. And here where I'm centering, we noted at the beginning, is 0. So I've got where I'm centering, my radius is 5. That's what that's saying. Okay, so I'm centered at 0 and I can go out 5 units in both directions and converge. Now let's talk about the interval. So I'm going to start with that last statement. Okay. But I don't want to write it in the absolute value form. Apologize, very large trash truck driving by my house. I don't want to leave it in the absolute value form. I want to break free of that. So I'm going to write this way. If the absolute value of x is less than 5, then that's the same as saying negative 5 is less than x is less than 5, right? Okay. And there I really start to see my interval. I go from negative 5 to 5, but, if I draw that line, I don't know if this is really necessary for people, but right, there's our radius, there's where we're centering. We know we're converging in here. But the question is, what about the endpoints themselves? Are we converging at the actual endpoints? Okay, we don't know. We have to test those individually. What does that mean? Okay, and I've got this note here. Endpoints x equals negative 5 and x equals 5 are unknown. Check each separately. So let's begin with the positive. X equals 5. I'm going to take 5 and I'm going to plug it into my original power series. And I'm just going to show you everything here. Seems like my camera is extra fuzzy today. I don't know if it's the afternoon lighting. A little sunshine coming in and making it hard to pick up all the letters. So when I plug 5 in for x in my original power series, I get 5 to the n there. And it happens to be the series n equals 0 to infinity, 5 to the n over 5 to the n. Okay, so, well, obviously that simplifies to 1. Whenever you check the endpoints, it's very, very common to get this sort of simplification. And this sort of simplification is not unusual because it's the endpoint, it's this like critical number. And so a lot of things tend to cancel out there. Okay, so this happens to be 1. Now, does that series converge or diverge? Well, obviously you see my work over here. Now we can fall back on those tests that we know. So we use geometric series test already. But here, hey, if I take the limit of 1, I get 1, but that does not equal 0. So this diverges by the divergence test. Okay. As soon as we plug those in, now any of those previous tests that we learned could come into play. Although we're really going to see themes with a few of them. Divergence test is a good one. Okay, so it diverges at 5. So back up here, we know that it does not converge at 5 itself. But what about negative 5? We need to test that on its own. Well, I'll just show you what I've got here. Turns out that's going to diverge as well. Let's see it play out. So if we plug negative 5 in for x, I'm raising that to the n. Okay. Negative 5 to the n. This is going to simplify, but how? Let's think of that as negative 1 to the n times 5 to the n. And then we can cancel these out nicely. And so this boils down to just n equals 0 to infinity, negative 1 to the n. Like, ooh, okay, it's an alternating series, I guess, but it's we never saw one that simple. What do? Well, it turns out, same idea as the last one. Just take the limit. That limit does not exist, right? It jumps back and forth between positive 1 and negative 1. The terms do. So, well, it does not exist. Sure doesn't equal 0. So this diverges as well by the divergence test. So both of our endpoints turned out to diverge for this example. So our interval of convergence, we're going to just leave those as parentheses. The interval of convergence is from negative 5 to 5. If we hit the endpoint itself, we diverge, but anything between there will converge. Now, what's kind of fun to do, I won't do it here for us together. If we were in class, I would do this. So I'll just encourage you. Go back and take a look at that original series, okay? Maybe find the first 3 or 4 or 5 terms of it, okay? So keep the x, but plug in n equals 0, n equals 1, like find like the third or the fourth or the fifth partial sum, okay? And graph that and just see what happens as you move further away from 0 as you get out to about 5. And you'll start to see the graph, you know, really start to, like, if it's curving, then it really like takes a turn like at 5 or negative 5. Kind of like our graph of that intro example. Okay, I'm going to stop this lecture here. We have one more example of radius and interval of convergence in the last video. See you then.